All right, the music comes down. That's our signal to get going. All right, welcome to my little talk. I kind of want to make this talk sort of pull you out of the bubble that most of us as Java developers, JVM users, have gotten trapped inside. That we can only consume things that are written in Java and only things that have been ported to Java or are provided to us by the platform. That's all that we ever touch. But there's this whole other world out there. So we look at our world here, living on the JVM, writing JVM languages, probably mostly Java, but more and more other languages. We have this wonderful managed runtime. It keeps us safe, keeps us from walking off the end of arrays, keeps us from dereferencing null pointers, all that stuff that we get used to that we love having in this secure environment. It helps us do development better, it helps us build applications faster, it reduces a lot of the debugging cycle because we're not trying to chase down seg faults all the time. So we get a lot of great advantages from this platform. However, it's also very tricky on this platform to get native performance out of libraries. There's a lot of tricks you have to know, there's a lot of anti-patterns you have to write to really get C or C++ level performance out of code that you're writing. It's also very difficult to access native operating system features as they come out, as they're introduced in Linux, Windows, OS X, whatever. We always have to wait for the JVM developers, the JDK folks, to go in and write the appropriate wrappers around those, decide what sort of overcomplicated API they want to put on top of it, and then release it to us as users to try and figure out how to dig back down to the one function call that we're actually trying to make at the operating system level. And then, of course, the C and C++ world, the native development world, is always moving forward just like we are. It sucks for us to have to wait for someone to port their libraries, port their code over, and then once you've ported the code over, what happens? It's a separate project. It lives separately. There's libraries and tools and utilities in the native world that we'd like to be able to access and be able to keep up with their day-to-day development, have the newest version of those libraries. And so I wanted to bring up it didn't. Oh, it's a little laggy. Interesting. I wanted to bring up the Java SE eye chart, which continues to grow year by year. Hopefully, with some of the modularity, we'll be able to start knocking some of this stuff out. We have a large array of APIs. We have a pretty good environment for building certain types of applications, at the very least. But the problem is there's all this stuff at the bottom, underneath the JVM, underneath Hotspot, that's very difficult for us to get access until we have blessed APIs that are given to us by some higher power. File system features like a lot of the NIO2 stuff, network sockets other than the ones available on the JDK, Unix sockets, ICMP stuff, interactive subprocesses. Anybody done any serious process management or process running on the JVM knows how bad these APIs are, how difficult it is to have a subprocess controlled by your Java application. Native GUI libraries, crypto libraries like NaCl, which has become very popular recently, the libsodium stuff. Accessing native memory, being able to allocate large blocks of native memory, maybe dealing with more data than we can fit into a standard Java array. 2 gigabytes is not very much anymore. So we need to have ways of accessing larger blocks of memory that the JVM can't support. And on. Hardware peripherals, especially when we start talking about how we're interested in the Internet of Things, we're interested in embedded Java, we're interested in the newest peripherals, Thunderbolt devices, and so on. None of this stuff we get for free. We have to wait. And maybe it's Java 9, maybe not. Maybe it's not going to get in there. Maybe it's not until Java 10 we're going to have access to some of those new features. That is a problem. That's a serious issue with the way that we do development on this platform and the fact that we're lagging behind probably the other half of the development world that's out there. And this actually has kind of spawned some interesting problems in Ruby, in implementing Ruby on the JVM and JRuby. There's a lot of file system level features you need to be able to have. You need to have good sub-process control, being able to access a lot of these libraries, trying to find some way that if there is a C library you need to call, there's an easy way to wrap it. All of these things that we've had to support in JRuby to be part of the Ruby community, very difficult to do on top of the JVM. Let's look at how we would typically do this in a traditional Java environment. So we've got some call that we want to make into a native library. In this case, we're just going to try and get the PID, the process ID of the current process. Maybe we need to put it into a file somewhere for a monitoring tool of some kind, a God or a monet sort of thing. We've got our user code at the top. we know we need to call some target library. In this case, it'll be libc with a getPID call. First thing we do is we write our user code. We write our little JNI thing. We'll go into the Java code right there. And for anybody who has never had to write JNI, this is deceptively simple. That's all I have to do, right? Just stick a native on there, and now I can make native calls down to some function below. But the story gets a little bit more complicated. With this, we have to run a separate tool that generates a lovely C header file, and it just gets worse from here the more complicated your signatures are and the more native signatures you need to deal with. You have to fill in the blanks there. Ultimately, what we actually want is about 8 characters of that file. The rest is all just boilerplate that's there for JNI, and this is probably the dead simplest case of a JNI call you'd ever do. And then even beyond that, you've got to figure out how to build this right. You have to either build it for all the platforms you're going to support or provide instructions and hope the user is able to build it for themselves. God forbid they might be on Windows and not have any build tools at all. So obviously this is not feasible if we're going to be loading in an entire GUI library or a crypto library or an arbitrary new library that comes out tomorrow we want to play with. It's too much effort and too much work for us to go through all this. I think John Rose from the Hotspot team kind of summed this up best. If non-Java programmers find some library useful and easy to access, it should be similarly accessible to Java programmers. And that's what we want to do. And the way we're going to get there is via a Java API that can pull in native libraries, manage native memory, and make native function calls, all from Java without having to write any native code. If you're not familiar with these libraries, this kind of seems like a pipe dream. This is the bubble that we've been told we have to live in. It has to be written in Java, 100% pure, right? If we're not pure, we're not doing good software development. But I think we can do a lot better than this. I think there are cases where we need to have access to these libraries, need to be able to make native calls and deal with native memory. And so the main library I'm going to talk about today is the Java Native Runtime. And there's the GitHub project for all of the GitHub organization for all the sub-projects. So the Java Native Runtime is a Java API, plain Java API, for calling native code. Native function calls, loading native libraries, allocating and managing native memory. Supported by a set of rich runtime libraries, libraries that pre-bind some things for you, libraries that handle similar sorts of operations like sockets and whatnot. Is anybody here familiar with JNA, the Java Native Access Library? Very similar to JNA, except way better and much faster. A lot more features and a lot better performance, and I'll get into some of those details later. So if we go back to our typical way of calling native code, we start out with our JNI version here, and really the problem is that we have to write code on both sides of this line. That's the real issue. If we could just write the user code up at the top that makes some call, have a library take care of all the native side of things, we wouldn't need to worry about the C side of it. We could just be Java developers or Scala developers or whatever, and be able to use all these other libraries that are out there. And that's basically what JNA and JNR do. Instead of writing the stuff at the bottom, you only have to write your user code at the top, and maybe a little bit of interface definition for some stub that represents a C call or C library. Maybe you need to define a structure, a layout in memory that represents some block of memory for a C function. And that's it. Everything from user code or so on down is handled by the FFI library. We get a stub at the top that gives us an implementation of some interface representing that C library. The JNI implementation at the bottom gets generated on the fly, so you don't have to have a C compiler, you don't have to write the separate code for it, and it all goes straight through. And on top of this, if you're using JNR, it's actually considerably faster than using JNA. If we look at our getPID example, this is really all that's involved to get a getPID call from Java. You don't have any special build tools. You don't have any libraries you need to build and ship. Your users don't have to worry about any of that stuff. As long as there is a C library with a getPID function in it on that system, it'll find it, load it, and you can call it as if it's a regular Java call. So that's the simple example of how we can get into JNR and start using native libraries more directly from Java. So let's talk a little bit about the way our layered runtime, the features that we provide as part of all the JNR projects. We'll start from the bottom here with libFFI and work our way up through a few of these utility libraries. Now, libFFI has been around for a long time. Pretty much every platform except Java provides some FFI layer. Most of them use a libFFI in some form. Python, Ruby, there's pinvoke on .NET. Every platform that's out there can make easy calls down into native functions except ours, which is really sad because there's a lot of great native code out there that we could be using. As I say, it's been around for a while, first released 1996. And it's basically a library that pulls in some .so, .dll, whatever. You can bind any of the functions that are named in it, the symbols that are exported, say what the inputs are, what the outputs are, and then call it programmatically. You get a function object as a result. So that's the baseline for what we need to be able to do. We've got the library at the C level that can do this stuff. JFFI is where it starts to get into the JVM level. This is Java Foreign Function Interface. This is the low-level API that we use to wrap immediately over the top of libFFI. A very small amount of code, very raw interface. It's essentially just a basic libFFI wrapper, bringing it up through the JNI level into Java code. So you won't necessarily deal with this. The reason I bring it up, though, is because we've made a great effort to try and support as many of these platforms out of the box as possible. You can essentially put any of the JNR projects in your Maven file, or whatever dependency system you're using, and it will pull down the native library that goes along with it, unpack it where it needs to go when it needs to run that native library. Does anybody have a platform that they deploy on that is not here? I'd be very surprised. I'd be very impressed, actually. Any OpenVMS or AS400 folks deploying? I can't believe that there's actually OpenVMS people. The interesting thing about this list is that these are all platforms where we have live JRuby applications in production. There are actually OpenVMS-based JRuby apps. Who knows what OpenVMS is? Yeah, see? That's why it's amazing that there's actually still people deploying stuff on there. I'm sure they get paid a lot of money to do it. All right, so we're going to move up a layer. As I said, JFFI is not the layer you're ever going to touch. It's just raw invocation of a function pointer somewhere in memory and some marshalling of data back and forth. What you're going to see, in the equivalent to JNA, is JNR FFI. This is the user-oriented API. This is what you'll access to define some bindings for a C library, define some structure layouts, and then call and access those functions directly. Now, I mentioned various reasons why not JNA. We started using JNA to implement some of these features in JRuby. The first thing we ran into is that it wasn't really low enough to build other FFI layers or other APIs on top of it. You can't get at the guts of JNA if you want to do more raw function calls or direct memory access. You kind of have to go through their definitions of here's a structure, here's a set of functions. That's as low as you can get. So if you need anything special that JNA doesn't provide, you're kind of stuck. It doesn't have any support, library, runtime, anything for preprocessor constants, macro stuff that you might have to deal with in header files, in C files. Just about every API that's out there defines some constants in a header file that you need to pass in for socket types or what modes to open a file in, things like that. If you don't have access to those constants, you still have to do the work across platform to figure out how to map them to the right values. We're doing that for you as well in JNR. The standard API sets was a big one. We started building an API called JNA POSIX. We'll talk about the JNR version a little bit later. Essentially trying to bind all of these functions that we kept having to use, symlink operations and so on. JNA didn't provide any of those. It was still just the basic layer. At the time, it did not support callbacks from C back into Java, which you need for APIs that get a function pointer, for example, and the performance was terrible. I'll show some graphs later that show how we've improved that. Now, moving up from JNR FFI, we've got that layer, and if you've got your own library, some internal code, crypto library you want to access, JNR FFI is where you would start. However, if there are libraries that we've already provided for you, you may not have to do even that much work. I mentioned the preprocessor constants. We have a library called JNR constants, where those constants that are defined, like socket types and whatnot, across various platforms, are generated into enumerations, Java enumerations. All you need to do is go in and get jnr.constants.socket type. And you get an enumeration that represents all of the native socket types on your current system. in a way that you can pass right back out to the native code and have it match what you'd get if you compiled the C code. So you don't have to do all that preprocessor stuff. You don't have to have a compiler available. Generate these once on a given platform, and then you ship it as a regular Java file. It says generation tools here. The generation tools are basically some really trivial Ruby scripts. You define what the library, the header file you want to pull in is, what the function names are, and it spits out Java code for that platform, represents those values as an enumeration. There are a bunch that we provide out of the box. These are ones that we've run into that we've needed to support Ruby features or other native features. I mentioned the socket type. Sock.java there is an enumeration for all the socket types. Protocol families for other types of protocols over sockets. File control flags. What else is interesting here? TCP flags for different types of TCP operations, and so on. Things that you're going to need once you get down to that level. And if there's a set of constants that you need, we could certainly add them here, generate them across a couple platforms, and we're ready to go. This is what those enumerations look like in the generated code. Here you can see that we're generating a Linux mapping of the sock constants. Those are what the values are on Linux, maybe different on another platform. You go and generate the same code there. We hide it all behind the scenes, so all you do is jnr.constants.sock, and it maps it to the right Linux or OS X or Windows or whatever. All right. So given that, an example of using those constants, here is a snippet from a Unix socket channel that actually can create a Unix socket that is a plain old NIO channel. The socket call, native.socket here, is the interesting one. And you can see in there we're using the protocol family constant for it's a Unix socket, it's going to be a streaming socket. We get our socket out of there, a type of socket that was previously impossible to access on the JVM. And then this code will go on later and basically set up the NIO channel around it. I'll talk about that library in a bit. Now, I mentioned pre-binding a whole bunch of functions. JNR POSIX is a slowly growing set of all of the POSIX functions that we've needed access to. Very easy to add others. Somebody just added get host name, so you could actually have access to the raw get host name from the operating system level. It's, like I said, it's mostly been driven by what JRuby uses. To a lesser extent, Jython folks have also wanted to pull in some of these functions, and so they've added a few things. We'd love to have basically 100% of POSIX bound into this library. So everything that you could do in a standard C application at the kernel level, you'd have all of that stuff available to you. We do have a partial pure Java backend to sort of mock out some of those functions, but it's getting more and more difficult to map them since so many features at the POSIX level have no equivalent on the JVM. This is a small subset of the functions that we expose in this right now. Some particularly interesting ones, again, getPid here. You're not going to have to go write the code to do JNR FFI to do getPid if you want it. You can just pull this library in. chmod, chown for other types of mode changes or ownership changes that NIO2 doesn't even give you. Actually accessing the raw native environment. Priority for processes. Getting raw native CPU times. It's very difficult to get user, system, and real time all at once in any of the Java APIs available. POSIX spawn, which I'm starting to use pretty heavily, gives you access to probably the most useful POSIX function that's out there for spawning a subprocess, redirecting its I/O, opening up files for it to dump data into, and so on. And then, of course, the fun one up here, forking the process, which does not work. You cannot fork, at least OpenJDK. There are JVMs that can fork, but on OpenJDK, it blows lots and lots of stuff up. I encourage you to try it. It's kind of entertaining to see how badly you can crash the JVM with forking. Okay, so moving on from there, now we've got all these raw functions. We want to be able to start mapping some things into standard Java objects, standard Java wrappers. JNR ENXIO, Extended Native Cross-Platform I/O, is basically a set of NIO channels, standard-looking NIO channels, selectable channels, that are simply backed by a native file descriptor and native function calls to read and write from that file descriptor. And then gives you all access to the full set of file control flags, lets you do selection on I/O types that you wouldn't have been able to on the JVM normally, like subprocesses, like standard I/O, and so on. The main library, the main class that you get out of this is native socket channel. And you can see, construct a native socket channel. All you have to give it is a file descriptor. Optionally, you can give it some selection operations that are valid for it, reads and writes and so on. And then from there on, it's just the channel. It's a regular old channel, but it wraps a native file descriptor. And if we look at an example of actually using this, this is a snippet of code from JRuby where, because we can actually use ENXIO and get these native channels directly, we rewrap standard in, standard out, and standard error in much richer channels. We can do selects on these and wait for input from the user. We can access the raw TTY and do like curses and graphics and stuff if we want on the console. We can actually provide a console environment on the JVM that's basically impossible to do without having access to the raw file descriptors. And this is the only code you need. You get a selectable channel on standard in, for example. Very easy to use. Building on top of that, I mentioned the Unix socket library that we have and the support that we've been building there. Unix sockets are still incredibly useful. If you want to be able to deal with, so you bring in a Java application into an environment where they've got a MySQL or Postgres server, and you got sysadmins who insist that you're using the Unix socket because they don't want that database exposed on a socket anywhere in the system, or on an external socket. No way to do that on the JVM right now. This provides a pre-made NIO channel. If you go to the example, create a file, point it at some location, usually some temp file. .sock is the standard convention for Unix sockets. We'll delete that file when we're finished. We create our new socket address that wraps around that file path. We open a new Unix server socket channel in this case, and then tell that socket to bind to this file. Now we have in our hand a regular NIO channel, but it doesn't go over standard network sockets. It's using all Unix sockets, which can be faster, definitely, or can be more secure as well. And that's all there is to it. Again, pre-bound and kind of building on top of this whole layered runtime, so you have access to a lot of these native features. Now, I mentioned performance as being one of the big things that's better about JNR. We've done a lot of work to try and make JNR as fast as possible. At the very least, at best, we'd like to be as fast as JNI. Obviously, we're going through the JNI layer. That's kind of a limiting factor. But we want to try and achieve as fast as possible code generated from JNR. So we're generating bytecode stubs on the front end. There's invoke dynamic support. There's now upcoming is going to be Lambda support as well, so that we can do some of these function binding and use JVM level features to optimize them. As I mentioned before, the JNI code, the native code that maps on the C side, is all generated at runtime. And ideally, in the best case for making a call through JNR, it's really only about 2 or 3 hops until you're actually into the native function call. One for our generated binding on the JVM, one for the JNI stub, and then bam, you're right into the C code. It's basically as fast and as little overhead as possible, comparable to what you would if you wrote the C code and compiled it by hand. A little side note about how we're doing this, yet another JNR project that I'm sure all of you are going to run right out and start playing with. JNR x86 assembly is what you think it is. It's basically a Java API or DSL for generating, loading, and invoking raw assembly code. So for all of you who've wanted to play with assembly but didn't want to go find a macro assembler of some kind, you can just generate it through this. Okay. So if we look at the performance of this, this is JNA versus JNR, and it's not really a fair comparison. We actually have to kind of go with the better scale on this. It is roughly 10 times slower, JNA is. We've done a lot of work to reduce allocation along that pipeline, reduce the number of hops involved, do a lot of code generation, try to get it as fast as possible. Now, you can actually improve on that a little bit. This is JNR just doing a plain get PID call versus telling JNR that I don't need to know whatever the last error condition in the C code was. Normally, it will take the last error, save it off into a thread local somewhere so that you can access it. It's safe across threads. You know why the sock call didn't work or why your file open didn't work. And that can actually get you another 25% or so. And then comparing with some of our real enemies as far as trying to get this thing out there, the top one is JNR get PID without the optimization. The red circles there, the second one down, is JNI. So if you wrote the JNI code and generated it and did all the compiling, that's where it comes as far as performance. And for a reason I have not actually quite figured out, and this was consistent over a number of runs, the code that we're generating on the Java side and on the native side actually ends up being faster than doing the JNI version of this same application. Seems impossible, right? I would imagine that the assembly code that we're doing at the native level doesn't have to do as much frame juggling, doesn't have to do as much of the JVM gymnastics to make this call work. So we end up being even a little bit faster in that case than JNI. About as good as we can possibly get without some JVM stuff. Now that's the problem. Down at the bottom there, the green X's, that is GCC with optimizations level 3 making the same get PID call. Now, it's possible that a lot of the get PID calls are being optimized away. It's possible that it's doing some other trickery. But at any rate, it's doing a better job of making this get PID call as fast as possible. So we need to do a little bit more. And this is kind of where we're talking about some of the future stuff. If we look at what this actually does under the covers, hopefully everybody's had fun dumping assembly from the JVM. I know I do it every day. This is the assembly that leads up to the actual call to the getPID function. And the interesting bit is here. We've got our getPID, our bench getPID, and our getPID JNR example there. It's doing an invoke interface on the generated stub for getPID, and then that goes off into the JVM, and the JVM figures out how to route it down to some native function. Now, what we really want this to look like when we actually see the native call happening is something more like this. We want our getPID call from the Java side to basically compile and optimize as if we'd written it as C code. Bind it directly to the libc library or whatever library you're calling and go straight in. And this is actually possible. This is actually where we're going to start going. The way we're going to get there is by getting some JVM help to do this stuff. We need to have some sort of standard FFI API in the JVM. We need the JIT to get involved. Hotspot needs to know that we're calling from Java into a very specific, well-managed, well-controlled piece of C code. It's a known function like getPID. The JVM really should not have to do any magic for it. It should be a trivial call. We should be able to tell the JVM that, have it optimize all of our code, stick that getPID call directly into the generated native code from the JIT, and then go straight through. And if the JVM knows that we're making native calls and that we've got these libraries we're binding, it should be able to also pick up on security policies, maybe do some segfault protection for us, help us be better C programmers than C programmers, honestly. So let's make this happen. This step 1, which has been my conference circuit for the past year, is just to make some noise about this. Talk at a few events and try and tell people what they're missing, what libraries they could have access to, how easy it could be, how much easier it could be if we could get it into the JVM. So I gave a talk last fall at the JVM Language Summit on JNR, and the guy before me went up and talked about his library that was doing native object layout and native memory allocation and stuff like that. And he just got nailed with questions like, how are you going to keep this safe? We're going to blow up the JVM all the time. You're exposing this world to developers. This is horrible. And I think he might have taken all of their energy and anger, because I went up right after him, and everybody was really excited about this idea, especially the JDK guys. They were thrilled. Anybody that's ever had to look at OpenJDK code or write any of the NIO stuff or any of the things that have to touch native libraries, they absolutely hate it. They don't like JNI either. And honestly, no one likes JNI. And they would love to have something at the JDK level that they could use to be able to write NIO without using any C code and have it work across platforms. And that's what we're going to try and move towards. So that was very promising. Everybody's really excited. Even the JIT guys were like, wow, I really want to make this optimized. as they're wont to do. That's what they sit there and do all day is, I want to optimize something. They just don't feel right unless they're optimizing all the time. So the step 2 then was to get a JEP, a JDK enhancement proposal, so that we could at least have at the OpenJDK level an internal API. So, for example, now.2 is a perfect example. If we wanted to add more features to that in Java 9, we wouldn't have to go and write the C code for it, make sure it's compiling and working right across all platforms, just have to write the Java stuff. Start being able to enhance the JVM with those native features we've been missing without making it even bigger as far as C and C++ code. Make it stay in Java code so that normal humans can actually get in there and work with it. So an FFI at the JDK level, usable for JDK features at least at the beginning, and kind of a baseline API, the core API of what an FFI for the JVM would be. And luckily, this is a JEP that I proposed, and it was approved about a month later. So this is now an official OpenJDK proposal. The next thing is to turn that into an OpenJDK project, and that's ongoing right now. John Rose proposed both the name and the project. Panama, I think, is a nice image of bridging two worlds. He's thrilled about getting going on this, and I think a vote went through and this has been approved. The artifacts for it are not up yet. If you go to look at the OpenJDK page, Panama's not there, but it probably will be pretty soon. We're working out who's going to run things. Like John wants me to do it, and I want John to do it, and we're not quite sure who's going to do it yet. This is the overall project for the JDK stuff. This is where there'll actually be an OpenJDK / whatever, Panama that you'll go to, just like you would have gone to for Lambda or anything else to play with those features ahead of time. And then we'll start throwing commits in there, probably based on the JNR library. I also should mention at this point Wayne Meissner, the guy who did most of the lowest level native JFFI, JNR FFI stuff. He is also going to be participating in this. He's going to do a lot of the technical work, and he's really excited to start working with the JIT guys directly to make this stuff fast. And this is where we're going to start looking into the questions of security, stability, platform support, getting it part of the OpenJDK build. So anywhere you've got OpenJDK, you're going to have an FFI layer out of the box. And it's going to be one of the best ones out there, ideally. So step 3, which is not underway, we need to get the JEP going. We need to have prove out some code, get it into the system, and see how it feels with the rest of the JDK. This is to be done. Again, not quite sure who's going to lead this, but it is going to happen. We're going to try and push this through as a Java 9 API. Just kind of getting going on this now since we just had the Java 8 release. The biggest thing here is that we want to hear from people that have used these native APIs, JNA, any of the C libraries, have played with JNR. Find out what sort of functions, what sort of features is it that you need at a native level. What are the problems that you've had dealing with it? Maybe performance is the only one. Maybe there are aspects of the API that are complicated to use. One aspect that I know I can think of off the top of my head is that sometimes those mappings are slightly different across platforms. Structs are laid out differently. Functions might take ints on one platform or longs on another platform. That's the kind of stuff where maybe generation tools would be good. So we can generate all of that JFFI code or JNR FFI stuff. You'll just get a piece of Java code out of that maps to every platform as you need to. So anybody that starts playing with this stuff or anybody who's done native access in the past, definitely ping me and we'll find a way to make it even better. So now how can you help here? Again, letting us know what you need is one big thing. If there's any native calls that you've ever wanted to make, or if you've ever wanted to play around with even just plain POSIX functions. Play around with making raw socket calls. Do some security hacking. There's lots of fun stuff you can do once you get down to the native level. Try out JNR. If you don't have a specific feature you're interested in or something you want to play with, helping us kind of clean up the library, add a little bit more documentation. It's a little sparse right now. All that stuff would help us get this into a condition to move it into OpenJDK as a sub-project. Successes and failures, any things that you've done with native libraries in the past, things that you've wanted to be able to do at the JVM level but didn't have access to. We want to know about all that stuff. And everybody should know at least one person who's had to make a native call or had to write JNI in their life. Go out and find that person wherever they are in university and tell them that they don't have to go down that path anymore, that there's a better way. I keep hearing from people that thought that, oh, still it's JNI, it's the only thing I can do. They don't even know about JNA. We got to get the word out that that's the wrong direction to go for the platform. There are better ways to call into these libraries. I guess I went with a pretty good amount of time here. I got lots of time for questions. I'll move on to this. The only other thing I would say here is that if you've never played with any of these native libraries, it's fun to try and cross that boundary, go into the C world and see what they're doing with stuff. One easy way is to go into the Ruby world, Python world, some of the native languages and the stuff that they're doing. You never realize how many things we're actually missing when you stay inside that bubble. And this is an easy way for you to break out of that, start trying to play around with some different things. Thank you. So we've got plenty of time for questions if anybody has interest. Yes, up here.
You showed us a list of different POSIX system calls, and among them were exit, PE, or even fork, although you said it doesn't work. So the resolving process, will it run within the JVM or as a native process?
Well, so the question was about some of the more let's say violent C calls that you can make, like exec, which will replace the current process. They will essentially act as if you'd written them in C code. So exec, for example, it's going to replace the entire JVM process. Threads are all going to get shut down, and you got a new process in place. So if you ever wanted to do a JVM tool that starts up, checks some system things, and then spawns or execs an application, works great. You don't have to have both of those processes in memory. You just take over the same process space. I mentioned POSIX spawn, which gives you pretty much the best raw access to a sub-process. Have access to inputs and outputs, have access to what environment it gets, user IDs that it runs as, all sorts of other flags that you can set for it in a single call, and then be able to use that. I'm actually working on essentially a process builder clone that builds on top of POSIX spawn. It'll give you a regular Java lang process if you want it, but you might be able to cast that into super process and have access to a whole bunch more features, a bunch of stuff that you would not get out of a standard process builder and may never get you can do with this API. But yeah, they basically do work like if you did them in the C call. So fork tries to start a separate process. That's where the JVM gets all screwed up because it doesn't have its GC threads and JIT threads with it. Exec will replace the current process, and POSIX spawn will give you access to it. Yeah, other questions up front. C++ and COM support. So C++, for anybody who's never done C++ at the binary level, you may see different mangling of the symbols exposed from dynamic libraries, not just depending on which C++ compiler you use, but which version of that C++ compiler you use. It's very difficult to make down calls into C++. Right now, if you did the mangling yourself, you can certainly bind those functions. We have some people that have basically said, this is my platform, this is my compiler, it's a C++ library, and I know how all these functions are mangled. No problem. At that point, it's just a symbol in a library somewhere. You feed it an object pointer, and it works like it's C++. Most of the folks that are interested in the FFI JNR work that we're doing in OpenJDK realize that C++ is a big part of this, and that we do need better tools to generate some bindings that do that mangling for you. Again, since it's going to be kind of compiler specific, there's only so many tricks we can use. Wayne Meissner, the guy who's done a lot of this work, he has a new project that's underway called JNR Clang, which uses the Clang compiler library, libclang, to generate bindings for all this stuff. So now I said it's so easy. All you have to do is write the bindings. Now you don't even have to write the bindings. You can use JNR Clang, point it at a header file, and you get Java files out that are basically JNR FFI wrapping all that stuff for you. It's early days, but JNR Clang actually generates itself. It does all of the libclang bindings automatically generated. So it's pretty cool. We do know that we want to do C++ support. It's going to be kind of a question of how much time and how much effort goes into making C++ interfaces easily accessible. You mentioned COM. The one thing about COM is that with pure virtual classes in C++, generally across libraries, across compilers, those are accessible directly. The mangling's the same on them. That might be a lot easier. A COM interface on the JVM wouldn't have to do as much of the platform-specific mangling. Well, it's also one platform. So that might be easier to do in the short term than doing a fully functional C++ binding. Yeah, the reference counting and stuff, I mean, once you're dealing with a native object out there, you're kind of going to be in charge of that. We do have in JNR FFI some auto pointer stuff that when it gets GC'd, it will finalize eventually, and then eventually it'll clear that memory out. But once we get down to the level where it's self-managed memory, it's self-managed memory at that point. You would be doing your reference counting interface calls up and down, and wrap it with some other utilities if you want, but that's about where we'd stand with it. Peter.
What about security stuff like setuid? Because I wrote some Java Unix library 12 years ago, or even in the last century, that sort of did JNI stuff. So if you were using setuid, then it would change the whole JVM process.
Right. Well, and these are the sort of things that getting the JVM guys involved is going to help with. Using native calls to bind signals, using native calls to make modifications to the process. There's a chdir that's bound into JNR POSIX. What happens when you actually change the running current directory of the JVM? I don't know. There could be all sorts of crazy things that happen when you change the dir out from under it. And the application that's running on the same server probably is not going to be thrilled about that either. So those are the sort of questions that we're going to explore. These are kind of going to be professional tools for professionals in some cases. We will, there may be some memory protection things that we can do, protected modes you could run in to test that things are actually safely accessing all the pointers that they deal with. One of the thoughts I had, and this is an open question, right now in the Java security model, you can limit what dynamic libraries will get loaded into the process. Anything not in that permission list doesn't get loaded. We could even go more fine-grained and say, this library, this symbol, and only whitelist the symbols out of those libraries that you want someone to be able to pull in. Again, that's something that if we had this as a JVM API, we could say, yes, you can pull in all of libc, but you can't call fork. Things along those lines.
And another way I thought about it is if you could spawn another JVM somehow, and it's only tiny, say you can then become a root access for this tiny JVM. I guess that requires more JDK modularity things going on.
Yeah, it might. I believe the POSIX spawn function allows you to at least pass on setuid, pass it on or clear it. You can make it a normal process at that point. So if you had a root utility that started up and spawned it using POSIX spawn, you can pass on that root setuid to it, where I don't think that the process builder will pass on setuid flags. It clears all that stuff. So again, having access to more powerful APIs, it opens up some holes, but it also lets us do a lot of things that we simply can't do otherwise. Yeah, next back.
Java long process, you talked about it, about the really bad and inefficient. You mentioned you're working on it. What's the chance of it getting like a physical API that makes it harder to shoot yourself?
Well, I would love to, along with all the other 1,000 projects that I'd like to do, I would like to actually get like a raw process builder or a process builder 2 API into JDK at some point. At the very least, there will probably be a JNR process very soon, because I just went through weeks of work on mapping Ruby's process management into POSIX spawn calls. So there'll be a JNR process that's very similar to Process Builder. But this stuff will be coming along, and we'll try and get it in as standard as possible. Does that answer your question?
Would you be doing it more high level, or would you do the
Well, so honestly, the JNR POSIX code that does POSIX spawn right now is pretty clean as far as a Java API. Granted, you get a PID out of it, which is meaningless to the JVM unless you can wrap that in something with wait PIDs and other stuff, the native calls that go with process IDs. But you pass into POSIX spawn a set of objects that represent redirecting I/O, standard in, standard out, redirect into a file, redirect standard error into standard out, easy things like that. The process flags, signal management, all that stuff that you can set is just another simple DSL that's in JNR POSIX. Ideally, we'd like this to be high level enough that you could take process builder code and swap this stuff in, but then maybe have some more professional interfaces underneath that let you actually poke that process a little bit better, do different kinds of weights on it, send it signals, things like that. Stuff that you need to do to actually control processes. Right, right. Oh, in the back.
I was going to mention on the process level, there was actually discussion on core libs dev within the last couple of months about Java Lang process API changes to JDK.9, which also involved people asking for use cases and feedback. So if there was something that you specifically wanted Java Lang process to do, then the core libs dev mailing list in OpenJDK is probably a good, read the archive and some feedback if there's something specific.
Excellent. So for the recording and everybody else, there have been some discussions on the OpenJDK core libs about improving Java Lang process. What they're really looking for right now is use cases. So if you're interested in better process control and process management on the JDK, now is the time, because we're going to make this happen and we want it to do everything that people need. Question in the back there? Or was over there somewhere? Any other questions? There.
What tools, process, and platforms do you use for your performance testing?
I've put it in a loop with current time millis is pretty much what I've done so far. Nothing too advanced. I haven't done anything at the native level to see if there's more opportunities there, like running with a shark or something like that. This is, again, someplace that if you're more familiar with native level function profiling or performance profiling, that's the kind of stuff that we could apply to this and see if there's any holes. Wayne he knows more about this low level JNI managed interface kind of stuff than anybody I've ever met. He has done a lot of that iteration. I don't know what all tools he's used, but John Rose, who's written several FFI layers himself for various types of VMs, he said that Wayne's FFI stuff is the best he's ever seen. He's really impressed with it, and there's almost no question that that's where we're going to start for the standard API in OpenJDK. Time for one or two? Anyone else? All right, great. Thanks very much.